Distance-time graphs seem incredibly simple at first glance, but they contain a hidden mathematical trap that destroys grades every single exam season. Today, we will decode these graphs perfectly, and I will show you exactly how to bypass the brutal unit conversion traps for full marks. Imagine a sleek, aerodynamic red hypercar sitting at the starting line of a massive straight desert highway. The engine roars, waiting to launch. The lights go green. The hypercar violently launches forward, pinning the driver to the seat, reaching a terrifying steady top speed in mere seconds. Suddenly, the driver hits the brakes, bringing the vehicle to a dead, frozen stop for a tire change before violently blasting off again. How do we mathematically capture that chaotic energy? We pivot to the strict IGCSE physics model using distance-time graphs. We place time firmly on the horizontal x-axis. As the clock ticks forward, the car distance from the start climbs up the y-axis. When our hypercar locks into cruise control at a steady, unchanging velocity, we say it is moving at a strictly constant speed. On our graph, this constant speed creates a perfectly straight, diagonal line. There are absolutely no curves, just a pure, linear mathematical relationship. Now, let us race two cars. The red car travels much faster than the blue car. How does the graph visually show this difference? Look at the steepness, or the gradient. The faster red car has a radically steeper slope. A steeper slope always dictates a larger speed. The slower blue car produces a much shallower slope. It covers significantly less vertical distance for every horizontal second that smoothly passes by. Next, our hypercar hits the pit box. The tires stop rolling. The vehicle is completely stationary, but the timing clock never stops ticking. Because the distance is no longer increasing, the graph flatlines. A totally flat horizontal line is the universal physics symbol for a stationary object. Real life is rarely constant. When the driver crushes the throttle, the speed increases rapidly. We call this physics phenomenon pure acceleration. An accelerating object produces a line with an increasing slope. The graph bends upwards into a sharp, aggressive, perfectly smooth curve. What happens during heavy braking? The car is slowing down, entering a state of deceleration. The overall speed is dropping second by second. Deceleration forms a curve with a decreasing slope. The steep line gently bends downwards, gradually flattening out as the car loses its forward momentum. Recognizing shapes is great, but examiners demand hard numbers. You must physically calculate the speed directly from a given straight diagonal line. The golden rule is that speed exactly equals the gradient of the line. The mathematical formula is change in y over change in x. Delta E represents the total vertical change in distance. Delta x represents the total horizontal change in time. We simply divide them. This brings us to the most dangerous examiner trap on the entire syllabus. Over 60% of students fail this exact exam question. A train travels 8 kilometers in 6 minutes. Calculate the speed in standard meters per second. The graph looks incredibly simple, right? A rushing candidate immediately divides 8 by 6, getting 1.33. The examiner brutally stamps a massive red 0 on the page. They walked blindly into the fatal unit trap. Look at the axis labels. Distance is locked in kilometers and time is trapped in minutes. Physics demands standard SI units. We must absolutely multiply 8 kilometers by 1,000, giving us an exact distance of 8,000 meters. Next, we shatter the time trap. Multiply 6 minutes by 60. This yields a precise delta x of exactly 360 seconds. Now, we safely substitute into our gradient formula. Speed equals 8,000 meters divided by a strict 360 seconds. Punch that into your scientific calculator. The train is moving at exactly 22.2 meters per second. Full marks legally secured. But wait, we are not safe yet. There is a secondary trap hiding in the gradient calculation that ruthlessly destroys precious accuracy marks. When students calculate delta y and delta x, they often draw a tiny, miniature triangle tightly clustered around just two nearby data points. Miniature triangles amplify reading errors. The ultimate examiner hack is to draw a massive gradient triangle using the entire straight section of line. Let us lock these concepts into your brain with a final multi-stage journey. A student walks to the park to read books. The first diagonal section shows a constant walking speed. Then, the line flatlines perfectly horizontally for exactly 40 continuous minutes on the x-axis. This flat section means the student is sitting absolutely stationary on a park bench, completely lost in their book, traveling 0 meters per second. Realizing they are late for dinner, the student sprints home. The final section of the graph sharply angles upwards with a violently steep slope. This steeper slope mathematically proves their speed has drastically increased. A higher gradient always dictates a faster velocity in strict physics exam conditions. Finally, the examiner asks for the absolute total distance traveled. Do not overcomplicate this. Just look at the final peak of the graph. Trace a horizontal line from the final point directly left to the y-axis. It lands perfectly at 0.6 kilometers total distance. Always check your SI units, draw enormous gradient triangles, and remember that flat lines mean zero velocity. You are now exam ready. Protect your grades and secure your A-star. Subscribe to GetYourTutors.com for the most elite physics masterclasses available anywhere today.